The Smith Lecture Series was started in 1988 by the class of 1962 to recognize my late colleague, Julian Smith, for his contributions to chemical engineering. At the time of his retirement from Cornell in 1996, Julian had served a whole variety of roles in the College of Engineering and Chemical Engineering, and the most important one I want to single out for today's event is his role as director of the School of Chemical Engineering during a very critical 8-year period as the school transitioned from a primarily undergraduate focus to the powerhouse for research and education we are today. Now, it turns out this is the first J.C. Smith lecture series that I can't look into the audience and expect to see Julian, because many of you perhaps know Julian passed away last year at the tender age of 96. He was in good spirit at the time of his passing, and we got to reminisce about his contributions to many of our careers, including mine, where I read this classic book written with my colleague Pete Harriet. I know in the program it says they collaborated on the 7th edition, but I think those of you know that Pete and Julian collaborated on all editions of that book, and the work is a product of both of their efforts. So I thought I would do something complicated, as is my style, for this lecture, and have Pete just stand up and utter a few words of remembrance about Julian as someone who knew him beyond the boilerplate things I said, and someone who could provide additional perspective on this very long life and this very impactful life. So Pete.
Thank you. I got to know Julian, of course, when he was a teacher in the Human Operations Lab. I still have some of the reports that he and Trustee Rhodes corrected with vetting on them. And I took over that course for many years. And then I was pleased when Julian asked me to help with the unit operations. The unit was originally Badger, and McKay had took the unit operations of chemical engineering, and they broke up, and Badger found a pressure Panchero and didn't go anywhere. And McCabe had the wisdom to select Julian Smith, a graduate of Cornell and a chemical engineer at DuPont, who brought out the addition of McCabe and Smith. And I was here, but and helped with some comments on the 3rd edition. I was a paid contributor. And then when McCabe was too old to really do much more, he asked me if he'd like to join this as a regular paid author. So starting with the 4th edition, I added a chapter on adsorption, and then the next edition, another chapter on membranes. And so each edition through the 4th, 5th, 6th, and 7th, I added a chapter with some new materials, out of the problems. Julian and I were kind of working independently. He had contributed a lot to the back of the book with the cave crystallization and solid standing, and we agreed that that could be cut back. So he spent his time revising and cutting back heavily the material in the last chapters, while I was working heavily some of the material into the first chapters. We worked kind of independently. He also kept track of all the negotiations with the publisher and many numbers. How many books have we sold? Up to 500,000. So I let him handle that, and so we went our ways independently. The one recent time when we did collaborate, very good results, because I went to him with my nails on the song, and he was like a perfect in music. So he had a program and was experienced in writing music and excellent pianist, so that we spent some time together figuring out just where the words in the notes went on my Human Operations song. And so it came out a few years ago of words and music by Pete Harriet and arranged by Julian Smith. And so that's available as a complete sheet music form for those who for those who haven't seen it. There's also a copy of the Singing the Bells on the song on the file webpage.
Very good. You want to say anything?
Oh, no, I think that as the statement in your handout is correct. I am the third author in the seventh edition, but I want to make it clear that I contributed heavily to the fourth, fifth, sixth, and seventh editions, not just to the seventh. The book is still selling well. It's been translated into many languages. And my only regret briefly is that it's not used as the standard text in our undergraduate courses, except in the plant design course, where people can find very useful information on that. But it's one of the things I've enjoyed over the years to be able to contribute to this success.
Thank you. So thank you, Peter. So it's my honor now to introduce this year's lecturer. From the very first J.C. Smith lecturer, Byron Bird, persons selected for this honor by the school have all displayed that unique balanced commitment to the scholarship of chemical engineering research and teaching that we've come to expect from the very best Cornell faculty. Today's lecturer, David Allen, is a Melvin Gertz Regents Chair in Chemical Engineering at the University of Texas, Austin. He received his undergrad degree in these halls, maybe not this room, receiving his BS in 1979 in Chemical Engineering from Cornell, and his PhD in 1983 from Caltech. After a 12-year stint as a professor at the University of California, Los Angeles, he moved to the University of Texas, Austin in 1995. David's research interest falls broadly in the area of air pollution control, and you'll get to see quite a bit of it today. Among his most notable contributions to the field are his leadership of the Texas Air Quality Study, one of the largest air quality studies ever undertaken. Today we will hear about his efforts to use results from that study to develop understanding of emission profiles from oil and gas operations in the United States. Tomorrow he will present a second lecture titled High School Engineering, Courses, Content, Structure, and Implications that will highlight the educational impact that I mentioned before. David has authored 6 books and over 200 research papers in areas ranging from coal liquefaction and heavy oil chemistry to the chemistry of urban atmospheres. His work has been recognized with a variety of awards, including the AICHE Lawrence Cecil Award in 2000 and the 2009 Research Excellence Award from the Sustainable Energy Forum of the AICHE. It is truly an honor to welcome you back, David. Please join the podium.
Thank you. Well, it is indeed a great pleasure to come back to Ithaca, to return to Ithaca. There are a number of pleasures inherent in that, especially given the weather that we've had over the last couple of days. The beauty of Ithaca is one driver. Also to come back to honor the memory of Julian Smith, who I had in a class on industrial process chemistry in this building almost 40 years ago, is a great pleasure. And then to revisit times like this in front of Olin Hall. This is the summer of 1977. George Sheely is in the middle of this picture, if you can see him, and then circled in red there is a younger version of me taking courses here in the summer of 77. So it's a great pleasure to come back to Ithaca. Many famous people have returned to Ithaca, not the least of which are deliverers of the Julian Smith lecture, but probably the most famous person to return to Ithaca was Odysseus, who returned to Ithaca, and his voyage was described in Homer's Odyssey. Today I'll tell you about my own personal odyssey between the time I left Ithaca and returning here, perils and discoveries throughout. So let's look at this topic, emissions from oil and gas operations in the United States and their air quality implications. I think in this audience, just about everybody is aware of the great transformation that's occurring in the energy sector in North America, particularly in the United States, that has resulted in the United States becoming the top producer of natural gas in the world. These are data from the Energy Energy Information Administration, showing natural gas production from various countries around the world. And the U.S. surpassed Russia as being the world's top natural gas producer a couple of years ago. In addition, oil production has increased dramatically. This is oil production in the United States from the start in the late 1860s in Pennsylvania through the present time. And what you can see is that we reached a peak in the 60s and early 70s, and then a fairly consistent decline until 2008. When there was a dramatic resurgence in oil production in the United States. And again, as this audience largely knows, that's been largely due to the extraction of resources from shales through the twin technologies of horizontal drilling and hydraulic fracturing. All these changes have occurred very rapidly. I'm going to give you some sense of the rapidity of that change by looking at the production in one particular area and the well counts and well distribution in this Barnett Shale in north central Texas. But certainly the Marcellus here in this part of the country has seen similar very rapid development. So here you see wells. Initially, you can see the year on the top right. You see the location of the Marcellus here. The black dots through about 2005 are conventional wells, vertical wells. The red dots then are horizontal wells with hydraulically fractured operation, which really began in earnest in about 2005, but then really grew dramatically rapidly. So this is a rapid change, and that's the main point I want to make with this slide. With any energy development on the scale that we've seen with the shale resource extraction, we have a number of environmental issues. Land use, water quality, water quantity, seismicity, air quality, traffic, noise. My particular expertise is air quality, and so that's what I'm going to focus on today, is air quality implications of these transformations. And I'm going to look broadly at the natural gas supply chain. As we think about air pollutant emissions associated with oil and gas, both production and processing, we can think about a variety of different categories of air pollutants, and we've done work in all these areas. One is the release of compounds, especially volatile organic compounds. I'll call them VOCs in this presentation, as well as oxides of nitrogen. These emissions combine in the atmosphere to produce photochemical smog, most notably ozone, as well as other air pollutants. But this is one category of emissions that produces photochemical smog. There are other emissions that are directly toxic. And finally, there are greenhouse gases. So we've done work in all these areas. I'm going to try and give you an overview of some of the main findings of what we've been learning. You can look at the estimates of production of oil and gas, but you can also look at the estimates of VOC emissions and NOx emissions. These are data assembled by the Environmental Protection Agency through its National Emission Inventory. What I'm showing here is all a baseline of 2002, and you can see the rate of increase of some of these emissions that's actually been quite dramatic. Shown in the map on the right is where those changes in emissions are occurring throughout the United States, and you see it, of course, largely in the oil and gas production regions. I'll note that this dramatic increase, perhaps a factor of fourfold or more, is driven both by more complete reporting and also growth in activity, but there's a large uncertainty in many of these emissions, and that's what I'm going to touch on a bit here today. But the estimates are, and here I'm giving you estimates, that emissions are increasing. So what are some of the challenges in getting these emissions right and really knowing what's going on? Well, let's look at the case of the Barnett Shale, again in north central Texas. Just in the Barnett Shale, as I showed you with that mapping, there are more than 10,000 individual wells, on the order of now close to 20,000 actually. Some of them just produce natural gas, others produce both natural gas and liquid products. It's rapidly evolving, as you saw. There are many potential sources. They're geographically distributed. They vary over time for a whole set of different reasons. And all these emissions depend strongly on what equipment you have on the site, what are the operating practices, what's the nature of the gas being extracted, and so on. So a lot of variables, very difficult emission estimation problem. And so what we try and do is to couple the emission estimates with measurements. And there are multiple approaches for measurements. We've used all of these. And so I'm going to start in the middle left here in what is a measurement directly at an emission point. So here we're going out to various sites. We're making measurements directly at the emission points. I'll then contrast that with other types of measurements, often referred to as top-down measurements, where you might have an aircraft or a satellite looking down on a broad geographical region and getting a total of what the emissions are from an entire region. We've done those as well. And then there are intermediate scale measurements that can be made using mobile measurement devices downwind of individual sites or locating permanent sites. This is in the Barnett Shale. And measuring emissions at some centralized location. All of these provide information that we can use to test our understanding of the emissions, broadly referred to as top-down measurements and then bottom-up when we start directly at the emission sources. So lots of approaches for measurements. And so what I'd like to do is give you a sense of what some of the headlines are from what we've learned in our group at Texas for the last 15 years in really trying to understand emissions of VOCs, of NOx, of greenhouse gases, all along the oil and gas supply chain. And there's one dominant headline in all of these studies that I'm going to dwell on a bit here, and that is the role of what are coming to be called super emitters. And this is a general finding that's emerging from a great many studies of the oil and gas supply chains. So what's a super emitter? You're already familiar with this concept, whether you know it or not, in that it's been known in the air pollution community for decades that roughly 10% of the passenger vehicles on the road give us half or more of the emissions, and you've undoubtedly been behind one of these tailpipes at some point or another. And these super emitters in vehicles, I did a study on this for the National Research Council that was requested by Congress. They're caused by a variety of factors, including the age of the vehicle. Some vehicles are more prone to others than to being a super emitter, so these days think perhaps Volkswagen. As well as people who either intentionally modify the vehicles or get their vehicles modified somewhat unintentionally, or equipment malfunction. So lots of reasons for super emitters, all right, in the vehicle fleet. And in the oil and gas supply chain, we have the same thing. So super emitters are due to emission events. That may be due to batch operations, or it may be due to startups or shutdowns or periodic process upsets, but they're known to occur. And here's one occurring. This is in the Houston Ship Channel, so the body of water that you're looking at here is Galveston Bay. Here's an aerial view of one of the chemical manufacturing facilities along the Houston Ship Channel region, and this particular facility is having an upset. They're venting everything through the flare. The flare is generating a lot of soot. So the first really detailed analyses of super emitters in the oil and gas supply chain was done for downstream processing in Houston beginning around 2000. And I'm going to tell you the story of that and what we learned from it and the actions that were taken on that before we return to natural gas. So the story I'm going to tell you about is this Texas air quality studies. The first of these was done in the year 2000. I'll sometimes refer to this as TexAX for the Texas Air Quality Studies. And the concern was to provide a sound scientific basis on which we could make air quality decisions in Houston. So here's Houston on a good day. Here's Houston on a bad day. In 1999, the Houston-Galveston area passed Los Angeles as having the worst ozone air quality problem in the United States. By far, something out of like 50 top ozone concentrations in the nation that year, 48 of them were in Houston. And at the time, the state was grappling with the problem of how do you solve that problem. And when you do that, you come up with something called a state implementation plan that talks about how you're going to reduce emissions. The best scientific understanding at the time, looking at the balance of the known emissions of these VOCs and the known emissions of the nitrogen oxides, told us that all the emission reduction should be NOx. That was the solution. Get rid of the NOx. That was our best scientific understanding. And the amount of emission reduction that was going to be required was unprecedented anywhere in the world. The only technology that could do it was selective catalytic reduction on essentially every source. Costs would have been on the order of $5 billion a year, but then if you attempted to put a value on the public health benefits, billions and billions of dollars a year as well. So the stakes were enormous. We were about to implement in the state of Texas a state implementation plan that called for these dramatic NOx reductions. We wanted to go in and make sure that, in fact, that would do the job. Was that the best approach based on the science? Before we did these measurements, that was what the science told us. So what we did was to organize a large air quality field study. For those of you who don't work in this sort of community-based field, the way the air quality community works is because the atmosphere is such a complicated place, we tend to all come together and study together one geographical location. So what we did was pull together the funding to bring 300 investigators to the Houston area to simultaneously make measurements from a whole variety of platforms. Texas geography here. This is the outline of the state. This is Houston, the area we're going to be looking at. I'm not from Michigan now, but this hand you can think of as Galveston Bay. All right? And that's the body of water on which most of the chemical manufacturing is based in the Houston area. This area in white here is the Houston urban area. So all along the western shore of Galveston Bay and the northern shore, and then in an area called the Ship Channel that extends right into the heart of town, is where all the chemical manufacturing is located and petroleum refining. So we made additions to a large number of ground sites. We put out lots and lots of different types of measurements. What were we trying to understand? This is a little bit of a complicated plot, but let me walk you through it. So here's that same map of Houston, and here's Galveston Bay, so the Houston area. Each one of these little dots is an air quality monitoring station, so a permanent air quality monitoring station. Here's the same thing for Dallas. Okay, and if we look at how Dallas behaves like a typical urban area. So for photochemical smog, relatively low concentrations at night because it's photochemistry. And then as the sun comes up and as traffic begins to release emissions during the early part of the day, ozone concentrations go up relatively slowly, peak in the mid to late afternoon, and then as the sun goes down, decrease. Right? Typical pattern, each one of these lines is one of these individual sites. Here's what we have in Houston. Same general phenomenon, and I'll note that these horizontal lines are various federal and other regulatory standards. Okay, so if you go over the line, you're concerned. So here is Houston, and what we see is this phenomenon that you could call an ozone spike, what they tended to be called in this process was a transient high ozone event. So any given site, and these are each individual sites, you get a big spike in ozone and then a rapid decrease. Very rapid rate of rise of ozone. It's a little tough to tell what might be going on from this plot, but if you plot these same data spatially, here's what you get. So this is the evolution of a transient high ozone event. Here's the industrial source region. Here's the wind. Yellowish part is the urban area. And so we get a burst of emissions in the industrial source region. That creates this ozone hotspot. It then grows and passes over various ground monitoring sites and advects then downwind over the course of the day. Typical pattern of a transient high ozone event. So the question was, what's causing it? We didn't know. So one of the key areas that we wanted to address, one of the key uncertainties was, what are these chemical and physical processes that are leading to these transient high ozone events, resulting in rapid and efficient ozone formation? So what's causing these? So let's look at some of the data that emerged from the study. This was the coolest of the 5 planes in the study. This is a DC-3. It's great fun to ride in. It was selected because it can go low and slow. Okay, and it goes low and slow here, flying at about 15 to 1,700 meters, and it's flying along this trajectory here and looking downward. It has a downward-looking instrument. Here is Galveston Bay, and here is Houston, and here's this flight track that the DC-3 is flying, and it's got an ozone LiDAR, and I'd be happy to explain later what this is, but this is mapping ozone concentrations underneath the airplane. So we tend to think of the mid-afternoon as being a well-mixed period in the atmosphere, but what you actually have in Houston is these little pockets of extremely high ozone concentrations, and then just perhaps a few kilometers later, not very high concentrations at all. So clearly, very, very heterogeneous concentrations. So we got a physical picture of these pockets of high ozone concentrations and how isolated they were from this sort of measurement, this LiDAR measurement. What ideally you'd like to do, though, is go into one of these little hotspots and do some chemical sampling. And that's what another airplane did. So another airplane would fly right into one of these hotspots, and on this particular day there was a hotspot right in the middle of this region. So here you see the edge of Galveston Bay. This is the ship channel coming along, and the airplane was flying along this track, went through right through one of these hotspots. And what was happening to various concentrations, and here you see it go essentially off scale for ethylene. Okay, and so what we found in these hotspots, more than anything else, was relatively high, in fact extremely high concentrations of ethylene, propylene, butenes, and butadienes, light olefins, extremely reactive in the atmosphere. Nobody would have predicted that. So now we know that we've got this problem with extremely reactive alkenes producing very rapidly high ozone concentrations. What do we do with that information? Because it was immediately apparent after we collected all these data with these really high reactive hydrocarbon concentrations, that if all you did was reduce the NOx, you would never meet the federal air quality standards. So I spent about 18 months of my life putting together thousands of pages of documentation that eventually got summarized in a little 5-page summary here. It was called an accelerated science evaluation because we knew what the stakes were, and we knew we wanted to publish our scientific papers But we also knew that we didn't want the state going down the road of implementing some regulations that we knew would not work. So we spent about 18 months getting a consensus of 300 scientists on an accelerated science evaluation. That's a lot of fun. So we did that. And here were a couple of conclusions, and I'll step you through some more conclusions. So these data indicated that the emissions of these highly reactive volatile organic compounds, ethylene, propylene, butenes, and butadiene, were leading to high ozone concentrations in industrial plumes. And so as a result, our state environmental agency, the Texas Commission on Environmental Quality, or TCEQ, decided they would create an entirely new class of air pollutants, not VOCs, not NOx, but HRVOCs. The only place in the world where HRVOCs are regulated is in the Gulf Coast of Texas, separated out as a separate category of emissions based on this study. So how'd we get it so wrong? All right, so we see that there are these chemical and physical processes in the atmosphere leading to rapid and efficient ozone formation, and it's due to these HRVOCs. We would have been able to predict that if we had gotten the emissions right, if we knew what the emissions had been. But we didn't. We, in fact, were greatly underestimating what the emissions were. And in fact, you can then go into some of these plumes around the industrial facilities, look at ratios of pollutants, and the overall consensus that the 300 of us arrived at were that the measurements of these reactive gases to various other air pollutants suggested that we were underestimating the emissions by a factor somewhere between 6 and 10, or perhaps as high as 50. All right? We were simply missing the boat on what these emissions were. So what in the world were they? This began, so this process of identifying what the emissions were began a process that's still going on to identify the missing emissions. One of the technologies to emerge from this, I'll show you a couple of times over the course of this lecture, were infrared cameras. And I'm not going to have the opportunity to show you all of it, so I'm just going to go to perhaps the last few, and I'm going to turn down the lights for a moment so you can hopefully see this a little bit better. So this is an image in the IR. It's taken from a small handheld camera. These are taken from a helicopter, in this case flying over a barge in the ship channel. At the time, there were no requirements for reporting those emissions because they were in transit. Here are emissions over tanks. So I don't know if you can tell from that one, but that's a tank leaking all the way around. It's dark enough that you're not really even seeing the tank itself. You're seeing the actual thermal image of the emissions. Here you have a tank leaking at one of its seals. In a moment, we'll come up to one of my favorite images from this little clip. But we began looking at where all these emissions were, and we could begin at least with this new technology at the time. This was now 2005, so about a decade ago, of these infrared cameras. And it was extremely revealing of where the emissions might be. And what we found was we had small populations. You see one tank here emitting a lot more than all the others, and that they were somewhat episodic. I'm hoping my favorite image will come up in just a moment. And here it is. So here you have a breather valve on a tank that probably is about to release. Now, in any case, we began looking for these emissions. So we knew we had these super emitters. Are they going on all the time, or are they episodic? Are they only happening occasionally? After all, we saw these things as ozone spikes, right? So you might expect that the emissions are episodic. So one of the outcomes of the initial round of studies was to require more detailed reporting of emission events in the Houston area. Okay, and so based on the findings that we had from this Texas air quality study on emission variability, new emission event reporting began to be required in 2003. And what did we learn from this? Now, I'll point out this is all self-reported data with all the limitations associated with that. Nevertheless, let me walk you through this diagram. So this is over the course of the first year of reporting of emission events in the Houston area. Okay, so 8,760 hours in a year. This is hour by hour. What are the emission events? The red line here is the average emission rate. This is for volatile organic compounds. The red line here is for all the hundreds of facilities in the Houston-Galveston area. What are their average emissions over the course of a year on an hourly basis? And so what you see here is, on occasion, single emission sources that are at times up to an order of magnitude larger than all the other emissions combined of VOCs in the Houston area. And so we spent a lot of time trying to understand this. The total emissions here are not large. All right? They represent just 4% of the total VOC emissions. If you integrate the area under this line, it's tiny compared to the integrated area under these emission events. But when they happen, where they happen, they're a really big deal. We spent a lot of time trying to look at the characteristics of them. Are they due to startups? Are they due to shutdowns? Are they due to emergency events? How long do they last? Quick snapshot summary is almost all of them were reported to last for less than 24 hours, often only an hour or two. And we found later that critical thresholds would be a couple thousand pounds. So if you're getting a ton release of a particularly reactive hydrocarbon, you can influence dramatically the air quality in the area. And on average, we had those sorts of emissions in the range of 1,000 to 10,000 pounds 2 to 3 times a week in the Houston area. So, whereas in most cases for air quality, we tend to think of emissions as being relatively constant day to day or week to week, maybe a little bit of time of day variation for things like traffic and so on. In the Houston area, what we actually have is greatly varying emissions temporally. Here, the major difference between a bad air day and a good air day is the difference in the meteorology. Here, it's a combination of both the variability in the emissions and the variability in the meteorology. So if you're really going to understand this and what do you do about it, you have to represent things stochastically. You have to say, well, what's the probability that I have one of these events? And then how's the atmosphere going to process it? And then what's the probability that I'll get various ozone levels? I'll just show you here. This is downtown Houston. These are maps of predicted ozone concentrations. Wind is blowing from your left to the right. And so here is normal emissions. We get a little bit of an ozone peak here, but now impose an emission event on that, and suddenly the emissions get a lot worse. So again, we communicate that information to our state environmental agency. And what do? Well, they put in place new reporting rules. They put in place a cap on these reactive hydrocarbon emissions, and then put in place penalties for various episodic emissions that are designed to reduce this. As we've gone forward, we've attempted to find ways to reduce these emissions. I'll just give you one simple example. So remember, I started with this image of a super emitter. This is an industrial facility having an upset, and what you see is all this black smoke coming from the flare sooting. If you were that operator, you really wouldn't want all that soot. What does an operator do when they have a really big flare and they've got a lot of soot in it? Well, you inject steam into the flame, okay? And that's a standard practice. But you can overdo that. Here is a steam-assisted flare, and all these are steam injection nozzles into the flame. And if you inject steam, water, into the middle of a flame, you're going to reduce the reaction temperatures, and you're certainly going to reduce the soot, but you're going to also reduce the combustion efficiency. And that's bad for other things that you're not seeing directly going into the atmosphere. How do operators control that typically? Well, they stick their head out the control room and see, what's the flare doing? Well, let's adjust the steam knob. How's it doing now? Let's adjust the steam knob. Not a whole lot of insight about what that relatively narrow operating regime is. So we spent about a year doing full-scale flare tests, trying to understand these operating regions, and then developed a whole set of operator training materials that would hopefully help operators better design their flares, also put in place control measures. So we can put in place methods to reduce these emissions. So all this seems like bad news, but this really is a good news story in that what we did was we had an extreme problem in Houston, all right, in 1999, in 2000. We identified the root cause using the best available science. We found it was super emitters of various types, especially of these reactive hydrocarbons, and then we implemented a lot of strategies to reduce those emissions. Same team, several hundred investigators, comes back 6 years later and does the same measurements again. What do we find? These are two locations where we saw the worst emissions in 2000, and then a very similar location. In this case, it's actually the waterway right next to the ground site that this was in 2006, 6 years later. I'm going to call your attention to this plot. This is a distribution of the ethylene concentrations that we measured during the study. What you see is the whole curve going from 2000 to 2006 is shifted to the left. Concentrations got a lot lower. But let me point it out to you here. On the very worst days, we went from having roughly 1% of our measurements that were above 100 parts per billion of ethylene, a really big number, to none above about 30 6 years later. We're still missing some emissions, we're still looking for emissions, but dramatic improvement in the ambient concentrations. And Houston went from having arguably the worst ozone problem in the United States to now not even having the worst ozone problem in Texas. Because we had the science that enabled us to make good decisions. So what were the benefits of these really large air quality studies? Well, one was just a more effective emission reduction plan. A second was more confidence by policymakers in the decision-making process. And I'll just pause here with a short anecdote. In developing air quality regulations, you go through a lot of public hearings. We had done our initial study in 2000. We'd spent 18 months getting a consensus set of scientific findings from all the investigators. And then in February of 2002, there was a critical meeting where our state environmental agency was going to make the decision. Do we stay with the old plan, or do we take all this science and use it and put it into a new plan? And in Texas, our environmental agency is run by 3 commissioners, one of whom serves as chair. The chair at the time was a guy named Bob Houston. And he opened the meeting in which this decision was going to be made, and he had our little executive summary here. And he waved it up in the air. And he said, I wish I had the exact transcript, but he said something to the effect of, every day I make multi-million-dollar decisions with 25 cents worth of data. And today we're going to make a multi-billion-dollar decision. And I finally feel as though I have enough information on which to base that decision. So for me, that was one of the most gratifying moments of my scientific career, was to give people the opportunity to have confidence in really difficult decision-making. Speaking very crassly as a researcher, another thing that this did was to illustrate to the state of Texas the great importance of having scientific information. In this case, it led to a better solution. It was also cheaper, but it did lead to a much better solution. And that resulted in the state of Texas creating its own air quality research program that continues to this day. So a lot of benefits to this. So we've talked about super emitters, and I've used the case study of super emitters in refining and chemical manufacturing as one part of the oil and natural gas supply chain. Another part of or environmental air quality issue that's gotten a lot of attention on the natural gas supply chain is the case of methane emissions. And we certainly have super emitters in this part of the supply chain as well. This is an IR camera image, that same technology that was pioneered in 2005 with the studies in Houston. In this case was making measurements of the IR signature of this leak in Aliso Canyon near Los Angeles of a natural gas storage facility. This single emission source was emitting at a rate equivalent to roughly the 20,000 wells in the Barnett Shale that were operating in routine operations. So certainly a very big leak. Integrated over the multiple months that this leak was occurring, they added about 1% to the annual natural gas supply chain emissions just from this one leak. But it's not just storage facilities. There are lots and lots of data that have emerged in the last 6 months or so in the literature giving us evidence. These two are from studies that I did. One saying that for a device called a pneumatic controller, about 20% of the devices give us 95% of the emissions. For these processes known as liquid unloadings, 3 to 5% of the wells give us the majority of the emissions. If you drive around the Barnett Shale and get emissions from each of thousands of facilities, you find that about 2% of the sites give you greater than 50% of the emissions. So moving forward, if we're going to take the next steps with methane and the natural gas supply chain, the same sort of steps that we did with VOCs in Houston, we're going to need to know what fraction of these emissions are super emitters and then what the super emitters are. What we're finding is that these emissions from the super emitters, how many of these we have and at what rate they're emitting, dominate the total for many, many source categories. So that's going to be our challenge going forward. There's a lot happening in this regard. I'd be happy to try and address questions regarding this, but in the spirit of keeping a few moments for questions, I'm going to briefly summarize here. That is that 15 or more years of looking at emissions along the oil and gas supply chains have told us that addressing super emitters is a significant part of the challenge as we think about having the lowest environmental footprint that we possibly can for our energy supply infrastructure. And the experience over the past decade or more is giving us a lot of information about strategies either that will work or that might not work. So with that, I'll close and see if I can handle what questions you may have. Thank you.
Any questions? Yes, in the back.
Seems like you have both hot spots and hot moments in your super emitters. If you're not doing continuous monitoring with, say, your IR cameras, how do you detect those hot moments?
Well, that's a big research challenge. And so I'll just point out that one of the research challenges being funded at a fairly large scale right now came out of ARPA-E, so the Advanced Research Projects Agency for Energy. And so they established a competition that's began about a year ago essentially saying we want you to develop, we want the community, being you, we want the community to develop new sensing technologies that would detect leaks at the rate of, for those of you who follow these things, 6 standard cubic feet per hour, or about a ton a year. And we want you to be able to localize that emission within 1 square meter. And we want you to be able to find it quickly enough such that, presuming you could fix it once it was found, that you would reduce emissions by 90%, and you have to do it at a cost per site, and here they were largely thinking of well sites, of $3,000 per year. That's the RPE challenge. They're meant to be hard. All right? They have lots of different technologies that are emerging for how do we find these.
Well, I'm curious, it's interesting to see, and very, very important, of course, for the people of Houston to solve this particular problem in Houston, but all this stuff that gets released into the air, then it's well mixed worldwide, and so there's a whole worldwide problem with these things. And to what extent do, I guess I'm wondering, does solving this problem help solve the world problem? And are there other super emitters, whole countries that are super emitters that dwarf this by comparison and are worthy of attention?
So that will vary pollutant by pollutant. So let's just pick methane then, because that's,
with methane?
well, that's a big issue. All right. So the question will be, what are the emissions for North America versus what are the emissions for example, Russia and their natural gas supply system? For those of you who are interested in looking at this in depth, there was a great review that was released last fall by Imperial College in London. They have something called the Sustainable Gas Institute, and they reviewed all the 400 or so publications looking both at North America as well as worldwide. And not nearly as much data over Russia as you might expect, but let me tell you how you might identify this. Sorry.
Is that because you can't fly over?
Well, remember our top-down included satellites.
Yeah,
So you don't. So here's an image of North America, and you could do the same thing for Russia, the former Soviet Union. These are from a particular satellite that was. It's been up for quite a while, so the technology has improved, so you could get better resolution. But this is showing prior to the shale revolution, the natural gas hotspot was in the US was in the Four Corners area, in what at the time was one of the largest natural gas producing regions in the United States, the San Juan Basin. And there are very good reasons why that's so, but the reason I bring this up now is you could get the same data over the former Soviet Union, get an order of magnitude estimate, and then track that over time. People at NASA currently argue that you can get this resolution down to 10 kilometers or so. So we could track globally, if we chose to, what these emissions would be, and have a sense of how the globe is responding over time. So lots of different approaches.
So no one wants to be a super emitter, right? And so I'm curious about, what sort of emissions that you need to monitor over chemical plants. And do you feel that the data you have provides complete coverage, or did you have to skip parts because of permissions and so forth?
Well, so let's break that question into multiple parts, and then I'll ask each sequentially. So first, certainly no one wants to be a super emitter or identified as a super emitter. And certainly a great many of these super emitters are due to malfunctioning equipment, in the same way that your car can become a super emitter because temperature sensor on your catalytic converter has failed. All right, so there are those that will be malfunctions, but there are also those that are occurring by design, since I have this slide up. The reason why this was a methane hotspot is because there's a process known as a liquid unloading that occurs in some gas wells, especially gas wells that have a lot of liquids being produced and that operate at relatively low pressure. This is one of the largest coal bed methane producing regions in the United States. And there are a large number of facilities that by design have these liquid unloadings occurring. But there are multiple companies working in the San Juan Basin with comparable numbers of wells, yet 95% of the emissions come from one company because they've designed their operating practices in certain ways. And so you can do that. If you go into a chemical manufacturing facility and you bring with you those IR cameras, you can get, with a skilled operator with those cameras, a very quick, immediate sense of what the emission points are. And so if it becomes a routine operating practice that an operator will have an infrared camera and in walking the plant at the start of their shift, does a quick scan of the plant, see what's going on, you have the potential to detect these things very quickly.
And so just quickly in terms of permissions, so did you need to get permissions to fly over, and what altitudes were you allowed to fly?
So in general, there are multiple permissions that you need for overflights. So something at an overflight, this is over the Barnett Shale, relatively small aircraft, something like 600 meters to 1,000 meters in elevation. No particular permissions beyond a flight plan necessary. But if you're going to go in low, or if you're going to fly a drone, or if you're going to go near the Houston Hobby Airport, or the Dallas-Fort Worth Airport, you need lots of permissions.
Jeff, wait a minute. Jeff,
Sort of a non-chemical engineer's question. I wonder about nonlinearity. There's certainly nonlinearity in dose response relationships in terms of what happens to people. You have people with a big pulse as opposed to the average that kill them outright. And I wonder about the impact of these chemicals, particularly the smog issues, in the atmosphere. I don't understand those dynamics are nonlinear. And therefore, are these spikes even worse than they appear?
Well, the results that I was showing you predicting what the magnitudes of the spikes were done using, that modeling was done using state-of-the-art science, community air quality models that are used around the world. There are basically 2 community models that are used to model regional air quality and include, albeit a simplified version of the chemistry, still one that contains thousands of chemical reactions, dozens to hundreds of chemical species, and then looks at the meteorology and the advection of the plume using an Eulerian approach, a gridded approach, breaking the region into very discrete subsections as small as a kilometer in scale. So we were doing these predictions, attempting to account for all those nonlinearities in what the emissions were. It wasn't a simple dispersion exercise. And that's the only way it would have been considered in the policy context, is if we used those same models.
Is the nonlinearity important? I mean, is there
Oh, absolutely. Absolutely. So for example, imagine that you had an emission source that were simultaneously emitting ethylene and propylene and butene. What you would see if you followed that plume in a Lagrangian sense downwind and could follow that plume along, first you'd see the most reactive of those species kick in, and then a little bit later the next one. And then you'd begin to see the effect of the reaction products, including formaldehyde. And so a lot of effects that get very complex in their temporal patterns.
So the point source and production end of this is one important problem that you're working on, David. But we hear a lot of rumors about the aging infrastructure. We have thousands of miles of gas pipelines, a variety of pressures. And is there a hope that you could get a quantitative measure of what those losses are? Because you've seen some of the numbers, which appear to be very high to me. Not so much from a point emission point of view, but from an aging infrastructure.
Yeah, Jeff, so as I know you're aware, but much of the audience may not be aware, There have been a series of studies that have been catalyzed by Environmental Defense Fund and then done in collaboration with companies that work along the natural gas supply chain, attempting to estimate what the leak rates are along the supply chain. The last of those studies have just been coming out over the last several months. And so here's a snapshot of what those releases were. We did the first of these studies that focused on the production part, and I came and talked about just that a couple of years ago. And what we found was that about 0.5% of the natural gas, on average, across all the sites, about 0.5% of the natural gas was leaking out at this stage. The next step is a combination of what's called gathering as well as gas processing. So gathering is where you take the output of multiple wells and bring them together into volumes that would be sufficient to economically do the gas processing. The gathering operations tend to emit on the order of 0.2% on average. There were some that had emissions as high as 10%. I'll also note we saw wells that emitted 10% of their production or more. All right, so all these categories are dominated by super emitters.
So what is the distribution function for this gathering versus the local distribution? Is it very narrow in terms of there's once in a while a bad case? Because I want to know what number to believe. You know, do I believe 0.1 to 0.2%? Is that what you're kind of implying?
So if you want, so if your interest is people refer to methane as a short-lived climate forcer, right. But in terms of regional photochemistry, methane's essentially inert. It's something that mixes on the global scale. It will have a lifetime in the atmosphere of a decade. And so it will get distributed throughout the global atmosphere. So if what you're worried about is overall that total that's coming out of the natural gas supply chain. Yes, it's dominated by these super emitters, but the best information we have about what the average over all of them are is shown here.
Okay,
all right. I'll note, however, one thing that, since you bring this up, that's a bit of a subtlety, and I didn't apologize for this equation that appeared at the end, but I put it up for a very distinct reason, because we face two very different problems going forward in terms of how we design research strategies. One problem is, what do we do if we want to solve the problem? Right? If we want to solve the problem, then we need to know what this fraction of super emitters are. We don't really care how much each individual one emits. All right? We know it's big. Fix it. All right? And how many are there? Where is it? Fix it. On the other hand, if you're interested in the overall global greenhouse emissions from something like the natural gas supply chain, you need to know what the average of these super emitters are. That's a really hard problem, because if it's 2% of the components and you need to get a distribution of those super emitters, you're going to have to sample thousands and thousands of sites. That's really hard. All right, so the challenge becomes, what are we trying to solve, and two very different demands.
All right, thank you. Thank you. I think we're going to have to stop there. So see you guys back here tomorrow. And I think David is going to tell us something totally different.
Totally different.
Yeah, and this is really exciting. There's growing movement and bringing engineering to high schools, and I'm looking forward to it. So see you tomorrow.